Now let us do chapter 10, which is on structure and bonding theories. You'll see things that you're familiar with here, but you're going to go in depth a little bit. We'll cover these learning objectives. The first learning objective is determining molecular geometry, followed by dipole moments, valence bond theory, hybridization mixing of sp-d orbitals, hybridization in molecules containing double and triple bonds that will dictate the electronic shape, of course, molecular orbital theory, molecular orbital configurations, delocalized molecular orbitals, and many more. So the first theory we're going to talk about is the verse pair theory, which is the valence for V, shell for S, E is electron, P is pair, R is repulsion. And this is a theory that was brought forth to explain shapes after Lewis discovered how molecules can be drawn in Lewis structures. Using VASPER model, we'll be able to predict the geometry of the molecule from electrostatic repulsions between electrons, which of course will be the lone pairs or bonding electrons. Okay, the first class we are going to look at here is the AB2 type of molecules. For example, look at carbon with two oxygens, where carbon will be your A, oxygen will be a B, so you have AB2. If you draw the Lewis structure of CO2, it's gonna get you this far with the carbon at the middle, so the A is in the middle and then the B are outside. Now, once you realize that you have an AB2 structure, the second thing you want to look is to count the number of atoms bonded to the central atom. Always the central atom is going to dictate the shape. So here is the central atom. Number of atoms bonded to the central atom is 2. So we count it as 2. Or you can call these bonding groups. Okay. And then the next thing you want to count is the number of lone pairs on the central atom. There's none in this Lewis structure, so 0. And therefore, these two are going to give you the total number of electron groups. So the total number of electron groups will be equal to the number of atoms bonded to the central atom plus the number of lone pair of electrons on the central atom. But we can also define electron groups in a different way. So one electron group is going to be counted as one double bond is one electron group, one single bond is one electron group, one triple bond is one electron group in whichever order, and then one lone pair of electron if not in resonance. We talked about resonances in the previous lecture. So if I'm looking at CO2, the central carbon, that's the central element. So I have a double bond to the left, count that as one electron group. Double bond to the right, one electron group. There's no non-bonding electrons to be considered. So total, this carbon has 2 electron groups total, which is the same thing you get here. If you count number of atoms bonded to the central atom plus number of lone pairs, which is 0, the total number of electron groups will be equal to 2. For me, I like counting electron groups using this information right here. One electron group is one double bond, one single bond, one triple bond, one lone pair, if not in resonance. Okay, so now the arrangement of electron pairs will be the bonding electrons and non-bonding electrons. There are only two electron pairs. 360 divided by 2 will give you 180, and the molecular shape the electronic shape is going to be linear. The molecular shape is going to be linear. Electronic shape is dictated by the bonding electron groups, the electrons in the bonds and the lone pairs. So these are the only two clouds of electrons I have in the two double bonds. So two electron groups will dictate electronic geometry. Electronic geometry will be linear. And I will tell you that if the central atom does not have non-bonding electrons, meaning lone pair, the molecular geometry will also be linear. For molecular geometry, you usually connect atoms. So connect the oxygen to the carbon to the oxygen, you get a straight line. That's linear. For electronic geometry, you count the electron groups, the bonding electrons or lone pairs. So there are only two. You see the electron groups are in the straight line. So again, it's linear. So it's linear. 180 degrees is dictated by the electronic geometry. And also hybridization, we'll learn about that. Okay, so you're given an example of beryllium chloride. If you are to talk about the electronic geometry, let me call it EG, you're going to count electron groups, which include bonds and lone pairs. The central atom is the beryllium. That's what caused the shots in shape, in terms of shape. So there are two bonding groups, the two single bonds. One single bond is an electron group. And therefore, since I have two electron groups, what someone will call regions, another person will call it a domain, 6 electron domains. 2 electron domains. Therefore, I expect that the bond is going to be 180. The electronic geometry for sure is going to be linear because you're just connecting the two balloons. They're on the straight line. So for the molecular geometry, this one you're going to connect atoms in space. And to connect the atoms in space is going to be the Cl, the Be, the Cl. So nothing is repelling these elements away. We'll talk about VSEPR very soon. So connect these elements in the straight line, still dictated by the electronic geometry. Bond angle will be 180 from here to here or from there to there. And therefore, I expect molecular geometry is linear. Anytime the central atom does not have a lone pair, electronic geometry is going to be equal to molecular geometry. And in this case, it's going to be linear for BeCl2. Molecular formula is BeCl2. That's an AB2 type of a molecule. Continuing with valence shell electron pair repulsion theory, let's look at AB3. We are done with AB2. I've given you examples. AB3 without a lone pair, an example is going to be formaldehyde. So the central atom does not have a lone pair. The central atom is the carbon. Okay. Now remember what I told you. If you want to determine the shape of this, you're probably going to follow these steps. The number of atoms bonded to the central atom is 3. Oxygen, hydrogen, hydrogen, so 3. Do you have any lone pair in the central atom? No. And then this will give you the total number of electron groups, which is going to be 3. Now, specifically, again, if you're counting electron groups, like I said, one electron group, I'll keep repeating myself, is one single bond. Okay. One double bond, a triple bond, and one lone pair of electrons that's not bonded, if not in resonance. Okay. So if I'm looking at this carbon, looking at electronic geometry, if I want to find electronic geometry, I'm going to look at electron groups. Here I have single bond, and a double bond. There are 3 electron groups there. Again, justifying our count here with no lone pair. When you don't have a lone pair, all these electron groups will be flat. So they're going to be planar, so to speak, flat on the surface. So we say planar. However, if you connect the tip of those electron groups shown by clouds, you get a triangle. So connect together triangle and planar. The electronic geometry is trigonal planar. Now, do you have a lone pair? No. So I expect electronic geometry to be equal to molecular geometry, and it's gonna be equal to trigonal planar. Now, for molecular geometry, I'll take my oxygen and my hydrogens and connect them in space. Still, I get a triangle that is flat on the surface, so it's trigonal planar. About bond angle, since there's no lone pair on the central atom, I don't expect much repulsion. These going around the circle is going to be 120, 120, 120, 120 degrees all around. Okay. So in this case, I've given you an example of kind of an AB3, where the central atom will be the A, the B will be the oxygen and the hydrogens, kind of. Okay. Another example that you can look at here is the boron trichloride. This one. This is boron trichloride. Okay. This one too, boron does not have lone pair. He will have a total of 3 electron groups, the 3 bonds. Connect them by tips. You're going to get trigonal planar. Boron does not have a lone pair, so EG, electron geometry, will be gonna be equal to molecular geometry. Now, one thing I want you to understand about VSEPR theory here. Lewis, the scientist, will have thought that these will sit like this in 90 degrees and 180 degrees here and 90 degrees here. That would be so wrong. Because remember, in between here you have electrons, and those electrons repel because they are equally charged. The electrons repel because they are equally charged. So they want to go and spread evenly in space. So instead of 90, the bond expands to roughly 120. And they're expanding because of repulsion of the valence electrons that are used in bonding. The electrons that are in the bonds in the 3 lines. So, which is why we call this valence shell electron pair repulsion theory that gives us these bond angles and shapes. Same thing with formaldehyde. Lewis would have thought that formaldehyde would be like this, with 180 degrees here, 90 degrees, and 90. No, you do have 4 bonding electrons here. You have 2 electrons here, 2 electrons here, which are equally charged, right? Negatively charged. So they repel. So instead of 90, the bond angle widens. So he widens to 120. So that is the application of valence shell electron pair repulsion theory, which helps us to dictate these bond angles and molecular geometry. So just like BCl3 would behave, you would expect BF3 to look the same. So these bond angles are going to be 120 degrees, and this boron right here has 3 electron groups, the 3 single bonds, there's no lone pair. Okay, if you roughly do 360 divided by 3, you're going to get 120 degrees around the bond, so bond angle. And the molecule is flat, as you can see, is flat here. If you want to visualize these molecules further, you can go to the link that I put in. So this link under chapter 10, if you click it, brings you here, and you can model your molecule. So for example, assume that the purple is the boron and these white balls are the fluorines or 3 chlorines. You see it's flat. If I click here, it tells me the molecular geometry is flat, trigonal planar. If I connect those white balls, I get a triangle. And then electronic geometry, you'll be drawing balloons on these bonds. there's no lone pair, those 3 balloons will be tied. Those ones will be tied on the surface. So it's gonna still be planar. The tips of the balloons will give you a triangle, so still trigonal planar. And the bond angle is roughly 120 degrees. Similarly, if you do that of formaldehyde, assume the purple is the carbon, this is the oxygen right here, this is the oxygen, and those are the 2 hydrogens. Then assume the purple is a carbon, so you'll see again it's also flat. Bond angle is 120. You connect the atoms on the outside, you get a triangle. So the molecular geometry is trigonal planar. We determined the carbon did not have a lone pair, so molecular geometry will be equal to electronic geometry. Electronic geometry, put a balloon or a circle this area where you have a double bond. Those are 4 electrons, electron group. And then there's 2 electrons here in the bond, 2 electrons there. You tie the balloons together, they should sit flat on the surface. The balloons there will be the electron clouds, bonding electron groups, still trigonal planar. The moment you add a lone pair, now the bond angle will change because of repulsion of these electrons and the lone pair with the bonding electrons. But anyway, we'll see that later.